Greetings, and welcome to the Philosopher's Corner. I'm Professor Hanson, and I hope you're doing well. Today's video will be an introduction to formal logic, Lesson 1. In order to understand the concept of formal logic, we can place it into the context of the two aspects of reality, the material aspect and the formal aspect. We become aware of the material aspect of reality through the perception of objects. We become aware of the formal aspect of reality through what we call the conception of ideas, which are about the relationships, typically, between the objects. In order to understand the material world, we develop what we call material logics, which include abduction and adduction and induction. The first two being the logics of material causality, and the third one, induction, being the logic of material analogy. In order to understand the formal aspect, then, we develop what we call formal logic, which includes only one type of logic, deductive logic, which is the logic of formal analogy, just as inductive logic is the logic of material analogy. With respect to the inferences that we draw with our logics, we say that material logics delivers logical contingency, which is to say the truth or falsity of the inferences are contingent or dependent upon the situation, of course, with the perception or with the objects themselves, with the material objects that we are reasoning about, understandably enough. For formal logic, we say that formal logic delivers logical necessity, which is to say the inferences that we draw will be either necessarily true or necessarily false. And we can do that because we are not dealing with the material world. We are dealing only with ideas, and in a sense we are playing with the ideas by using symbols to represent them and trying to find out that if we say that something is true, what else must necessarily be true or must necessarily be false? And this is what we call logical necessity. The discovery or invention, depending on your term, of formal logic is due to the Greek philosopher Aristotle, who invented symbolic logic by taking a Greek sentence that was a statement about the world and removing the subject and predicate words, the words that contain reference to the material world, replacing those with mere symbols, A and B, right? And therefore leaving, in a sense, just the symbols for the subject and predicate and the words that stand for the relationship between the symbols or the subject and the predicate. And so basically he removed the material content of the sentences and left only the formal content. Unfortunately, Aristotle made the assumption that Greek grammar embodied the logic that he needed to study, and so he developed his logic using basically the natural language, the Greek language itself. Unfortunately, that entangled him in the ambiguities of language, among other things, and so in the modern version of formal logic, what we do is introduce the formal language itself. Excuse me. As with natural languages, the formal language will have a lexicon, a collection of objects that we will work with in the language, and it will have a grammar, a set of rules for how we can work with these objects. Turning to that, then, we see that we have what is called the lexicon, the set of objects that we will deal with in our formal logic, and we have the grammar, which is sets of rules for using the objects in different ways. Beginning with the lexicon, then, we have a class of objects called operators and a class of objects called operands. These are similar to, for instance, the operator of addition, the plus sign, in mathematics, and the operands that are, of course, numbers, the things that are operated on by addition. Here, however, we have the logical operators, and there are 4 of them, and because the symbols for them always mean the same thing, we call them constants. These are logical constants, the first of which is what we call the position operator, and then the negation operator, the disjunction operator, and the conjunction operator. The objects that we use to operate on with the operations are, of course, called operands, and for us that will be a class of what we call propositional variables, lowercase letters of the English alphabet, and these special symbols. Starting with these, the lowercase letters of the English alphabet will represent any proposition whatsoever, and I will define a proposition directly. So P represents any proposition whatsoever. Q represents any proposition whatsoever. In addition, we have 4 special symbols that will allow us to assign logical value to the propositions. Basically, then, a proposition is anything that can be assigned a value of true, represented by an up arrow, or false, represented by a down arrow. And in general, the up arrow will represent any true sentence whatsoever, and the down arrow will represent any false sentence whatsoever. In addition, we will have need of the idea of sentences that are necessarily true or always true, and necessarily false or always false. And so we introduce symbols for them. Again, the up arrow represents true, but now with the equal sign, it represents necessarily true. And the down arrow represents false. And now again, with the equal sign, it represents necessarily false. Moving then to the grammar, we have rules of syntactics of the propositional forms, how we can combine the symbols to create new propositional forms or propositions. And we have the rules of semantics of the logical operators, what the meaning of these things are. Beginning then with the syntactics, which produce propositional form, consisting of a composition of operands and operators. We start with the position operator first, and we see that it requires a single propositional variable, and when we combine these, we get what we call a simple propositional form. Similarly, for the negation operator, we combine that with one propositional variable, and that too produces a simple propositional form. Because of the requirement of a single propositional variables, these operators are called monadic operators. With respect to the next 2 operators, they will require 2 propositional variables in order to create a new propositional form. And the way they are used is basically we set one propositional variable to the left and the other propositional variable to the right for both disjunction and conjunction, and those are legitimate compound propositional forms. Because of the requirement of 2 propositions here, we say that these are dyadic or binary relations. Moving on then to the meaning or the semantics, basically what we do is we define the logical value in terms of either true, the up arrow, or false, to produce the propositional content. And these will be explained or displayed in terms of what we call the logical matrices of Boolean operators. Before we move on to that, however, rather than start with 4 different operators as we have here, I prefer to start with a single operator that I will introduce directly, and then create these other operators out of that operator. In that way, we start with the most fundamental idea, and we nevertheless end up with the type of logic that is typically developed for modern formal logic. Turning then to those ideas, we introduce again the 2 logical values, the up arrow standing for true, and the down arrow standing for false. We talk about specific operands. Here we have P and Q, and again, each one stands for any proposition whatsoever. This, of course, will then stand for any other proposition whatsoever. Okay? And when we analyze the possible combinations of true and false for 2 propositional variables, because of course, as I said, a proposition is anything that can be assigned the value of true or false. When we have 2 propositional variables, if the first one is true, the second one might be either true or false. And so there are 2 combinations where the first one is true to allow for the 2 different instances of the second proposition being true or false. Similarly, when the first proposition is false, the second proposition will be either true or false. And so for two propositions, we will always have four possibilities of combining true and false of the assignment of the values to the propositions, and we will always list them in the order of true, 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 false, false, true, and false, false. Next, then, we introduce our single logical relation, that is the relation of incompatibility. It is represented by the vertical stroke here, called the Sheffer stroke. And the way we read this is P is incompatible with Q. We understand this to mean that not both P and Q are true. And of course, if we analyze the possible combinations of true and false with respect to P and Q, we find that the statement not both P and Q are true is actually a true statement for these three possible combinations, but it's false for this one because both P and Q are true. So to say not both P and Q are true is certainly false in this particular situation, although it is true for the other combinations. Okay? So that basically is how we understand the relationship of incompatibility. Next then, as I said, I will use the relationship of incompatibility to define the four logical operators, although basically the focus is the operators of and or, which are the more complex. Nevertheless, we will start with the first two and then move on to the more complex ones. The symbolism of the Boolean operators then, of course, again, is the double tilde for position, the single tilde for negation, what we might call the V for disjunction, and the inverted V for conjunction. Again, when we use these symbols in combination, or the operators, I should say, in combination with the operands, we attach a single operand to the operator position. We read this as P, and often we merely write that as P because since we have a negation operator, it distinguishes the positive from the negative. The negation operator, of course, works in a way similar to the position operator. We attach a single proposition to that. We read this as not P. For the binary operators then, of course, we need two operands, and so we read this as P or Q, as you see here, and then we read this as P and Q. As it turns out, as I said, we can define these operations in terms of the incompatibility relation, and that is what is displayed here with the symbols of incompatibility. Of course, to represent the position operator, all we need to do is place a propositional variable on the field that stands for P, of course. We could represent it this way or this way, and we will choose to do this. Right? And that is straightforward enough. For the negation operator, all we need with respect to incompatibility is to say that a proposition P is incompatible with itself. Again, we read this as not P and P, or not both and, right? And not both is the way we read incompatibility. Right? And so basically we can't have the truth of P, and so we need necessarily the falsity of P, or in other words, the truth of the negation of P. And so to say that P is incompatible with P can be represented by not P. With respect to disjunction, we find that if the negation, and we could certainly read this as the negation of P from this, if the negation of P is incompatible with the negation of Q, that means they can't both be false at the same time. Their negations are incompatible. Right? And so for the disjunction operator, we will find that if they're both false at the same time, this will be a false statement because they are defined as not both being false at the same time. Finally, for the conjunction operator, we say that P's incompatibility with Q is incompatible with itself. In other words, P cannot be incompatible with Q. Therefore, they must both be true. Okay? And so we will use the AND operator to represent that incompatibility situation in which both P and Q must be true. We can now move on to assigning true and false values to these operators. Um, as long as we understand that we are using them merely as abbreviations for the relationship of incompatibility, we understand that, of course, we are still using the most basic logical system. Moving on then, we introduce the logical matrix for position and negation. Basically, we have one proposition and its opposite, and so, of course, since any proposition can receive either a true or a false, we have only 2 rows in our table. Previously, we had 4 rows in our table because there are 4 combinations of true and false for any 2 propositions. But of course, for a single proposition, we only have the 2 possibilities. And so we say that if the position of P is true, the negation of P is false. And if the position of P is false, the negation of P is true. In other words, if P is true, not P is false. If P is false, not P is true. In this way, we create the polarity of opposite propositions. In other words, for every proposition, there will be its opposite, which is false when the proposition is true and true when the proposition is false, and vice versa. Moving on then to or, and as you recall, or stands for not P being incompatible with not Q. In other words, they can't both be false, or they both are not false at the same time. And of course, when we inspect the table here, we find that on the bottom row, both P and Q are false. And so to say that they are not both false at the same time is a false statement. Otherwise, it is true, because here they are both true. Here one is true and the other is false, and here again one is true and the other is false, but they are not both false at the same time. And so the statement P or Q is true in those situations. So again, P or Q will be false only when both P and Q are false. Otherwise, it will be true. Conversely, for P and Q, again, we recall that P and Q represents the statement that P's incompatibility with Q is incompatible with itself. In other words, they can't be incompatible. They must be both true. In other words, they are both true. And of course, when we inspect the table, we find that that is the case only for the top line, where we have P true and Q true. And so to say that they are both true is a true statement in this condition. Otherwise, of course, it is false. Right? And so P and Q will be true only when both P and Q are true. Otherwise, it will be false. Summarizing then, we have the basic simple propositional forms, position and negation, and they are related, of course, in this oppositional structure. And then we have the basic compound propositional forms, disjunction and conjunction. And we see that in a sense they are related as well, because again, P or Q will be false only when both parts are false. P and Q will be true only when both parts are true, and so they too form a type of opposition. This is the basic logical system, but although these operators allow us to combine propositions, they don't allow us to infer one proposition from another, which is, of course, what we need if we want to investigate logical necessity. Logical necessity says that if you say that something is true, often you can infer that other things will necessarily be true as well. And that's what we want to investigate here, logical necessity. So we need a form of inference that allows us to move from one proposition to another. As it turns out, the ancient Greek philosopher Philo of Megara introduced the notion of implication into his logic, and he defined it in such a way that an implication, such that P implies Q, or in other words, you can infer Q from P, this is the inference that we're talking about, P implies Q will be false only when P is true and Q is false, because of course then you're saying that a true proposition implies a false proposition. Philo Megara did not want to allow that situation, and so he said that that situation will make the implication false, otherwise it will be true. And so if P is true and Q is true, a true proposition implies a true proposition, and that is fine. Or if P is false, regardless of what Q is, the implication that P implies Q will be true because we assume that, or at least Philo Megara assumed, that we go along with them, that a false proposition will imply anything. And so to say that false implies true is true, and to say that false implies false is also true. As it turns out, this implication, or this definition of implication, is identical to the definition of a particular not or statement, a combination of not and or. So, as we see here, what we have is the statement or the proposition not P or Q. Right? This is, in a sense, not a straightforward disjunction because we are not given P here, whose values we are assigned over here. We are given the negation of P, and so in order to have the correct values to evaluate this here, we need to invert or negate the symbols here. Literally, we invert them. In other words, we turn them upside down. True becomes false, true becomes false, false becomes true, and false becomes true. We use then these values for not P along with the Q values to evaluate the OR statement. And of course, we recall that an OR statement will be false only when both parts are false, otherwise it is true. And so on the first line we have not P false, but Q is true, and so the OR statement is true. On the second line we have not P, again false, and now Q is false. Excuse me. And so the statement P, not P or Q, will be false because both components are false. On the third line, we have not P being true, and that automatically makes the OR statement true. And on the fourth line, we have the similar situation, and that automatically makes the OR statement true. At any rate, you see that the assignment of values for this not OR statement, not P or Q, is identical to the assignment of values that Philo Megara gave to the implication statement. So, in a manner of speaking, this symbol for implication is merely an abbreviation for the symbol, for the symbolism of this not or statement. So, in effect, he's not really introducing anything new. The implication can be reduced to the not or statement. The not or statement can be reduced to incompatibility. And again, we are dealing with the most basic logical system. However, we now have a statement that allows us to move from one proposition to another. We may infer Q from P if the true and false combinations are correct. Right? This actually, of course, is a one-way rule, right? But we find that by combining, in a sense, two implications, in other words, if P implies Q, but it's also true that Q implies P, we can combine both of those together, and we get what we call the operation of equivalence. Logical equivalence is the form of the identity principle, if you will, for logic, just as mathematical equality, the equal sign, is the identity principle for mathematics. What the equality sign says is that the magnitude of the two numbers that are equal, so if m is equal to n, then the magnitude of m equals the magnitude of n. They are equal. They're not identical, that's just a general idea, but here the identity is specifically equality. For the logic that we have here, we read this as equivalence. We say that P implies Q and Q implies P, and so that they are equivalent to each other. And here now what we're talking about is the logical value. We say that the logical value of P is equivalent or the same as the logical value of Q. And this is not, again, identity or equality, it's equivalence, saying that the values, the logical values, which are similar to mathematical magnitude, but of course not the same thing, here the logical values are the same. And of course, this will be a true statement only when the value of P is the same as the value of Q. And of course, when we inspect our table, we find that that is true when both P and Q are true, but it also happens to be true when both P and Q are false. So to say that P is equivalent to Q is true on the first line and true on the last line, but false on the second and third line because, of course, the values are not the same. Now we have, of course, logical operators that not only allow us to combine sentences, but to move from one sentence to another, or to say that I'm sorry, I should say propositions, not sentences. Two propositions, or propositional forms, strictly speaking, are equivalent. And that is all of the equipment that we need to start doing deduction. However, we need to talk about a few other ideas before, in particular, combining propositional variables and operators according to the rules to make more and more complex propositional variables, or propositional forms, I'm sorry. Right. So here are some examples of legitimate propositional forms. We start very simply with, for instance, not P. That itself is a proposition, so I could OR it, for instance, with Q, as I have here, not P or Q. And in order to show that that OR statement is itself a proposition, I place parentheses around it, parentheses not being logical symbols, but what we call metalogical symbols. They do not do any work in the logic except help us organize our ideas. But of course, since this now is a proposition, I can negate that if I want, right? And I can actually go in and that with, say, or to create an even more complex proposition. To show, again, that this is a single proposition, I can combine that with square brackets, right? And then I can use that perhaps as the antecedent, as we call it, in an implication, S here being the consequent. So basically we have one proposition here implying one proposition here. To show that this whole line is a proposition, again, we put the curly brackets around it, and then again we may use that as a single proposition in another relation. It may turn out that this proposition is equivalent, for instance, to not T. At any rate, of course, we can go on combining as long as we follow the rules, giving us one main operator with one proposition on either side at every step. Then all of the propositional forms will be legitimate propositional forms. And in fact, we could use truth tables, or I'm sorry, logical matrices to evaluate the truth or falsity of these, as we did, for instance, with this particular statement here. We did not assign the values of this OR statement as we did for the straightforward OR statement of P or Q. We had to evaluate not P first, and then we evaluated the value of the disjunction. Right? And so basically, in that step, we used the logical matrix not to assign the values, but to determine the values. And we could do that for all of these. However, as we saw when we had just a single proposition, we had two rows in our table, true and false. When we had two propositions, that doubled to four rows in our table, because of course there are four combinations of true and false for two propositions. As it turns out, if we introduce a third variable, we have to double that again. Our table then gets 8 rows. If we add a fourth variable, it'll be 16 rows, and a fifth variable would be 32 rows ad infinitum. So very quickly, the method of the truth tables, or logical matrices, strictly speaking, becomes very unwieldy. And so we turn to the method of deduction, which of course is the main objective of these lessons anyway. In order to do that, I need to introduce one more topic before we end lesson 1, and that is the notion of, again, a statement that is necessarily true. We will use the necessarily true form of equivalence and distinguish it from the mere form of equivalence, which can be true or false. We will insert an equal sign in it. This will still be equivalence. It will still say that the value of this is the same as the value of this, but as we will find out, this will be a statement that is always true, which we call a tautology. Here, it is easy to see that the statement is always true, because what we have on the left hand is, of course, just a disjunction, P or Q, and as with every disjunction, that will be false only when both parts are false, otherwise it will be true. And what we have on the right-hand side is the same disjunction with the operands in opposite order. But of course, changing the order of these two columns does not change the value of the logical true and false. And so we see that this disjunctive statement has exactly the same logical value as this disjunctive statement, so that whenever we ask, is the value of this the same as the value of this, necessarily they will be the same. And so the statement that says they are the same will always be true. There are only 4 possibilities of combination in true and false for these two things. Under all of those possibilities, this statement turns out to be true, and so it cannot possibly be false. It is necessarily true to say that P or Q is equivalent to Q or P, and that is what we call a tautology. As we will see in Lesson 2, we will develop a set of tautologies, some of them what we call formal equivalence, such as this, but others, or at least one of them actually, a type of formal implication, and that will constitute our deductive system. That then is the end of Lesson 1 for an introduction to formal logic. I hope it was edifying and I hope you enjoyed it. Thank you.